Close your eyes and let yourself drift upward, as we follow the gentle ascent of humanity's quest to rise above. In the beginning, there was only climbing. Imagine our earliest ancestors looking up at a cliff face, a tall tree, a steep hillside. To go up meant using your muscles, your hands and feet, your strength and determination. Every vertical journey was exhausting, dangerous, limited by the power of the human body. But humans have always been dreamers, inventors, problem solvers. And very early in our history, we began to wonder, what if we didn't have to climb? What if something could lift us? Let yourself drift back to ancient Egypt, around 2600 BCE. The sun beats down on the desert. You're standing at the base of the Great Pyramid of Giza, and workers are constructing this massive structure, one of the wonders of the ancient world. Picture the enormous blocks of limestone, each weighing 2.5 tons. How do you move these massive stones? How do you lift them higher and higher as the pyramid grows? The Egyptians used ramps, yes. Long, gradually sloping ramps that allowed workers to pull stones upward. But they also used something more sophisticated: primitive hoisting devices. Simple machines consisting of ropes, wooden beams, and pulleys. Workers would pull on ropes, and through mechanical advantage, they could lift weights much heavier than they could lift alone. Imagine the sound. Chanting workers pulling in rhythm, ropes creaking under strain, the scrape of stone against stone. As massive blocks inch upward, these weren't elevators in any modern sense, but they were lifting devices, humanity's first attempts to overcome gravity through mechanical means rather than pure muscle. In ancient Greece, around 236 BCE, a brilliant mathematician and inventor named Archimedes revolutionized our understanding of mechanical advantage. Picture Archimedes in Syracuse, working in his study, contemplating the problem of lifting heavy objects. He understood levers, understood pulleys, understood how forces could be multiplied and redirected. Archimedes designed compound pulley systems that made lifting remarkably easier. According to legend, he once said, "Give me a place to stand, and I will move the earth." His pulley systems were so effective that one person could lift an object that would normally require many people. These systems became the foundation for all future lifting devices. The Greeks used hoisting mechanisms in their theaters. Picture the Theater of Dionysus in Athens. During performances, actors playing gods needed to appear above the stage, literally Deus ex machina, God from the EU, machine. Stagehands operated a crane-like device called a machine that would swing actors through the air, making them appear to fly. The audience, seated in the stone amphitheater, would watch in wonder as Hermes or Apollo descended from above. Now let your thoughts drift to ancient Rome. The Romans were master engineers, builders of aqueducts and roads, creators of concrete and underfloor heating. They also created more sophisticated lifting devices. In the Colosseum, completed in 80 CE, Roman engineers built an elaborate system of elevators beneath the arena floor. Picture the hypodium, the underground network of tunnels and chambers below where gladiators fought and animals prowled. In these chambers, workers operated at least 28 different elevator shafts. These Roman elevators used a system of ropes, pulleys, and counterweights, all operated by human power. Men, or sometimes animals like horses or donkeys, walking in circles, turning capstans that wound ropes. The elevators lifted wild animals, lions, bears, elephants, up through trapdoors into the arena. Imagine being a spectator. You're watching two gladiators fight, and suddenly the floor opens and a lion rises up on a platform. The surprise, the spectacle, the engineering marvel of it all. These Roman elevators could lift around 600 pounds. Workers in the hypodium coordinated carefully. Timing was crucial. The wrong animal appearing at the wrong moment could ruin the show. Picture them in the dim underground, sweating in the heat, listening for signals from above, operating their mechanisms in precise coordination. The Romans also built vertical hoisting systems for construction and in some wealthy homes. In his Natural History, Pliny the Elder mentions that Emperor Nero had a private elevator in his palace. It probably operated on a similar principle: ropes and pulleys powered by slaves. Let yourself imagine being a slave tasked with operating an elevator in a Roman villa. You stand in a small room, pulling ropes in a careful rhythm. Above you, wealthy Romans ride the platform up to higher floors. Your arms ache. Your hands are raw. But you must maintain the rhythm, must lift smoothly, must not let the platform drop. Your entire job, day after day, is to lift others while you remain below. Breathe slowly now as we move through the centuries to medieval Europe. After the fall of Rome, much engineering knowledge was lost or forgotten. Europe entered what we call the Dark Ages. Though that term is misleading, innovation continued, just differently. Monasteries became centers of learning and craft. Monks preserved ancient texts, including works on mathematics and engineering. And in these monasteries, they built something special. Hoists for lifting supplies to different levels of their tall stone buildings. Picture a monastery in the 1100s, built on a steep hillside. The monks need to transport food, manuscripts, building materials between levels. They construct a simple hoist, a wooden platform attached to ropes that pass over a pulley at the top of a shaft. Monks in the lower level load supplies onto the platform. Monks at the upper level pull the ropes, hauling the platform up. It's slow, requires significant effort, but it works. It saves countless trips up and down stairs carrying heavy loads. The Abbey of St. Martin in Albi, France, built around 1150, had one of the earliest documented monastery hoists. Picture the thick hemp ropes, the worn wooden platform, the stone shaft it traveled through. The system lasted for centuries, monks pulling the same ropes their predecessors had pulled, lifting supplies in an endless chain of service. Medieval castles sometimes had hoists too, particularly for moving supplies. To high towers, picture a castle under siege. Food stores are kept in a high tower for safety. Workers operate a hoist to transport supplies. The alternative, carrying everything up narrow, winding stairs, would be exhausting and slow, especially when speed matters. Now, let your mind drift to Renaissance Italy, where Leonardo da Vinci, the ultimate Renaissance man, turned his attention to lifting devices. It's the late 1400s. Leonardo, with his insatiable curiosity, sketches designs for numerous mechanisms in his notebooks. Picture Leonardo in his workshop, surrounded by papers covered in his distinctive mirror writing. He draws a hoisting machine, powered by a crank. He designs a platform elevator with a screw mechanism. He conceptualizes systems that wouldn't be built for centuries. As with many of Leonardo's inventions, these remained theoretical, sketches in notebooks rather than physical machines. But they show that brilliant minds were contemplating the problem of vertical transportation, pushing beyond what currently existed. In 1743, at the Palace of Versailles in France, something remarkable was installed: a flying chair for King Louis XIII. This wasn't a public elevator, but a private conveyance for the king. Picture an ornate chair attached to a system of ropes and pulleys, operated by men stationed inside the walls and floors of the palace. The king could sit in his chair on one floor and be lifted to visit his mistress, Madame de Pompadour, whose rooms were on a higher floor. Imagine the luxury of this. Rather than climbing stairs, the king simply sits and is lifted. The mechanism is hidden from view. The king experiences smooth ascent as if by magic, while hidden servants strain at the ropes. This flying chair represents something important. Elevators beginning to emerge from purely functional devices into symbols of status and luxury. Let your breathing slow as we enter the 18th and 19th centuries, when everything begins to change. The Industrial Revolution transforms the world. Steam power, factories, iron and steel production, cities growing upward, and with these changes comes an urgent need. Better ways to move people and goods vertically. Picture England in the 1760s. James Watt is perfecting the steam engine. Coal mines are being dug deeper and deeper. Miners work hundreds of feet below. Ground and everything. Miners, coal, equipment, water must be moved up and down these shafts. Human-powered hoists aren't sufficient. The mines need more power. Steam-powered hoists begin appearing in mines in the 1780s. Imagine a steam engine at the surface, its piston pumping steadily, turning gears that wind cables around a drum. The cable descends into the dark shaft, far. Below, miners climb into a crude cage, just a wooden platform surrounded by metal bars. They signal to be raised. The engine engages. The cable winds up, lifting the cage. The miners ascend from darkness into daylight, swaying slightly, the cable creaking, the mechanism above them hissing and clanking. These early industrial hoists were dangerous. Cables could snap, platforms could fall. Miners understood the risks, but had no choice. Working in deep mines required these elevators. Death from falling platforms was common enough that miners became fatalistic about it. In factories, hoists moved materials between floors. Picture a textile mill in Manchester in the 1820s. 5 stories tall, each floor filled with machinery. Raw cotton arrives at ground level and needs to be transported to upper floors for processing. A cargo elevator, just an open platform attached to a cable, is loaded with bales of cotton. A steam engine powers a drum that winds the cable, lifting the platform. Workers guide it, keeping it from swinging or hitting the walls of the shaft. These early factory elevators were purely for cargo, never for people. They were considered far too dangerous. The platforms were open, just wooden planks. There were no safety features. If the cable broke, the platform fell. Workers understood. You might ride the elevator if you were desperate or foolish, but you did so at your own risk. Let yourself imagine being a factory worker in 1835 watching the cargo elevator descend. It's loaded with heavy barrels. The cable is old, frayed in places. You watch it descend, praying it doesn't break. Sometimes you hear stories. A cable snapping, a platform falling, crushing whatever or whoever was below. The productivity gains from elevators are undeniable, but they come with constant anxiety. Now breathe deeply, because we've arrived at one of the most important moments in elevator history. The year is 1852. A man named Elisha Otis, working in a bedstead factory in Yonkers, New York, is tasked with solving a problem. Elisha Otis is 41 years old. He's worked various jobs: wagon driver, doll maker, grist mill operator, mechanic. He's clever with machinery, good at solving practical problems. His current employer needs a hoist to move materials between floors in their factory. But they need it to be safe, or at least safer than existing hoists. Picture Elisha in the factory, looking at the elevator shaft, thinking about the fundamental problem. Cables break. That's the reality. Under constant stress, carrying heavy loads, cables fray and snap. When that happens, the platform falls. How do you prevent that? Elisha designs something brilliant in its simplicity, a safety mechanism. He attaches a wagon spring to the top of the elevator platform. From this spring, 2 metal ratchets extend outward toward the sides of the shaft. Normally, the tension in the lifting cable keeps the spring compressed and the ratchets pulled in. But if the cable breaks, the spring expands, pushing the ratchets outward into notched guide rails on the shaft walls. The ratchets engage the notches, stopping the platform from falling. It works. Elisha installs it in his factory. The hoist is now safer. His employer is pleased, but Elisha realizes this invention could be much bigger than one factory. This could change everything about elevators. In 1853, Elisha opens his own company, Otis Elevator Company. He manufactures elevators with his safety mechanism. But there's a problem: convincing people. The public has heard about elevator accidents. They're terrified of elevators. Why would they buy this new product? Elisha needs a demonstration, something dramatic, that will prove his elevator is safe. In 1854, at the World's Fair in New York City, the exhibition of the industry of all nations, held at the Crystal Palace, Elisha stages one of the most important demonstrations in industrial history. Picture the scene. A tall platform is erected in the exhibition hall. On it stands an elevator platform with Elisha Otis himself aboard. A crowd gathers below, looking up. Elisha signals to the operator to hoist the platform. It rises slowly, 10 feet, 20 feet, 30 feet above the crowd. Elisha stands calmly on the platform. Then he picks up an axe. Imagine the crowd's confusion. What is he doing? Elisha shouts down. All safe, gentlemen, all safe! Then he swings the axe at the cable holding the platform. The cable severs. The crowd gasps, surely expecting to witness a horrible death. But the platform doesn't fall. It drops perhaps an inch, just the slack in the spring engaging, and then stops. Perfectly secure. The safety mechanism has worked. Elisha stands on the platform, alive, calm, vindicated. Let yourself feel the crowd's amazement. The thing everyone feared most, the cable breaking, has happened, and yet the platform is secure. This changes everything. If elevators can be made safe, they can transport not just goods, but people. They can be installed in buildings. They can make tall buildings practical. The demonstration is brilliant theater, but it's also brilliant engineering. Elisha knows that seeing is believing. He could explain his mechanism all day, but watching a man cut his own elevator cable and survive, that's unforgettable. Orders begin coming in, not immediately. Change is always slow, but gradually. Building owners, factory operators, mine. Companies start installing Otis elevators with the safety mechanism. In 1857, the first passenger elevator with Otis's safety mechanism is installed in a 5-story department store in New York City, the E.V. Hofwout building at Broadway and Broome Street. Picture this first passenger elevator, a platform enclosed by iron railings, operated by steam power. The operator stands on the platform with passengers. He controls the steam valve, starting and stopping the elevator. It's slow. Lifting 5 stories takes about 1 minute. But it works. Customers and staff at the department store can now travel between floors without climbing stairs. The elderly, the infirm, pregnant women, people for whom stairs are difficult or impossible, can now access upper floors. This is revolutionary, though people in 1857 don't yet realize how revolutionary. Within decades, this invention will enable cities to grow upward, will create skyscrapers, will fundamentally reshape urban life. All because of a simple spring and ratchet mechanism that prevents a platform from falling. Relax deeply now as we watch cities begin their rise into the sky. Before safe elevators, buildings rarely exceeded 5 or 6 stories. Why? Because climbing more than 6 flights of stairs is exhausting. The upper floors of tall buildings were the least desirable, hardest to reach, often occupied by the poorest tenants or used for storage. But with safe elevators, this equation reverses. If you can ride an elevator, height doesn't matter. In fact, upper floors become more desirable. Better views, more light, quieter, further from street noise and dirt. The value of real estate in a building inverts. The higher floors become the most expensive. This realization, combined with other technological advances, steel frame construction, electric lighting, central heating, enables a new building type. The skyscraper. Picture Chicago in the 1880s. The city is rebuilding after the devastating fire of 1871. Land is expensive. The solution: build upward. In 1885, the home insurance building is completed, 10 stories tall, using steel frame construction rather than load-bearing walls. It's considered the first true skyscraper. This building has 4 Otis hydraulic elevators. These don't use cables and motors. Instead, they use water pressure pushing a piston beneath the elevator car. Imagine a giant syringe. Water is pumped into a cylinder, pushing a piston up, and the piston lifts the elevator. To descend, water is released from the cylinder, and the elevator lowers smoothly. Let yourself imagine riding in one of these early hydraulic elevators. You're a businessman in 1885, visiting an office on the 10th floor. You enter the elevator car. It's small, wooden-paneled, with a bench along one wall. An elevator operator, wearing a uniform, slides the gate closed and operates the controls. The elevator rises smoothly, surprisingly quiet. You feel a slight pressure in your ears as you ascend. Through the gate, you can see the elevator shaft, walls passing. The operator announces each floor. 2nd floor, 3rd floor, 4th floor, finally, 10th floor. The elevator stops smoothly. The operator opens the gate. You step out, 10 stories above the street, barely winded. A decade ago, this would have been impossible. New York quickly becomes the epicenter of skyscraper construction. The Equitable Life building, completed in 1870, has an elevator and reaches 7 stories, making it one of the tallest buildings in New York at the time. The Tribune building, completed in 1875, reaches 9 stories. The tower building, completed in 1889, reaches 11 stories and is considered New York's first true skyscraper. Each new building pushes higher. Each requires more elevators. The elevator industry grows rapidly. Otis Elevator Company becomes successful beyond Elisha's dreams, though sadly, Elisha himself dies in 1861 before seeing the full impact of his invention. By 1890, buildings are reaching 15, 20 stories. By 1900, some exceed 30 stories. This is possible only because of elevators. Imagine trying to climb 30 flights of stairs multiple times a day. Impossible for most people. But riding an elevator for a minute or two? Easy. Picture the Manhattan skyline in 1900. Buildings of various heights cluster together, some reaching dramatically upward. At night, their lit windows create a new kind of beauty. This vertical city wouldn't exist without elevators. The elevator hasn't just made tall buildings possible, it's fundamentally reshaped urban life. Let your mind drift now to another crucial innovation, the electric elevator. Hydraulic elevators work well, but they have limitations. They're slow, typically around 200 feet per minute. They're limited in height. You can only drill a piston cylinder so deep. For buildings exceeding about 20 stories, hydraulic elevators become impractical. The solution is electricity. In 1880, a German inventor named Werner von Siemens builds the first electric elevator. It uses an electric motor to turn a drum that winds the cable. Picture the elegant simplicity. Electricity powers a motor. The motor turns, the drum winds, the cable lifts. No steam, no water pressure, just clean electric power. But von Siemens's elevator is slow and primitive. The real breakthrough comes in 1887, when Alexander Miles, an African-American inventor, patents improvements to elevator door design. Then, in 1889, the Otis Elevator Company combines electric power with geared traction. The cable runs over a grooved wheel connected to an electric motor. This system is more efficient, faster, and can lift much higher. Picture an engineer at Otis explaining the new system. The elevator car hangs from one end of the cable. Counterweights hang from the other end. The counterweights roughly equal the weight of the car when it's half full. This balance means the motor doesn't have to lift the full weight, just overcome the difference. It's elegant, efficient. Electric elevators begin appearing in new buildings in the 1890s. They're faster than hydraulic elevators. Some reach 300, 400, even 500 feet per minute. They're smoother. They're more reliable. They enable buildings to reach even higher. By 1900, elevator speeds of 700 feet per minute are achieved. By 1930, some elevators reach 1,200 feet per minute. Let yourself imagine this speed. A skyscraper 60 stories tall. You enter the elevator on the ground floor. 60 seconds later, just 1 minute, you're at the top. The speed is exhilarating, slightly frightening. Your ears pop from the pressure change. Some people feel their stomachs flip as the elevator accelerates and decelerates, but speed creates new problems. At these velocities, starting and stopping must be smooth, or passengers will be thrown around. Engineers develop sophisticated control systems, variable speed motors, rheostats to control current, careful calibration of acceleration and deceleration. The faster elevators go, the more engineering challenges emerge. Air pressure in the shaft becomes significant. Fast-moving elevator cars push air ahead of them and create vacuum behind them. This causes buffeting, swaying, uncomfortable pressure. Changes for passengers. Engineers add air vents to shafts, design aerodynamic elevator cars, develop pressure equalization systems. Imagine being an elevator engineer in 1920, working on a new skyscraper. You're calculating airflow in the shaft, designing the shape of the elevator car to minimize air resistance, determining the optimal acceleration curve. Elevators have evolved from simple hoists into complex mechanical systems, requiring advanced engineering. Now, let yourself drift back to the early 20th century and meet the people who made elevators work, the elevator operators. For roughly 80 years, from the 1880s to the 1960s, most elevators required a human operator. Automatic elevators existed but were considered less safe and less sophisticated. Picture an elevator operator. Let's call her Dorothy. It's 1925, and Dorothy works in a department store in Chicago. She's 22 years old, wears a crisp uniform, usually a jacket and skirt in the store's colors, white gloves, sometimes a small cap. She stands in her elevator car, her domain, her small moving room that she controls. Dorothy's elevator has a simple control system, a brass lever that swivels. Push it forward, the elevator rises. Pull it back, the elevator descends. Return it to center, the elevator stops. Sounds simple, but it requires skill. Push too hard, the elevator accelerates. Too quickly, jerking passengers. Pull back too late, the elevator overshoots the floor. The goal is smooth acceleration, smooth deceleration, and perfect alignment with each floor. The elevator floor should match the building floor exactly, with no step up or down. Dorothy has been operating this elevator for 3 years. She's developed a feel for it, knows exactly how much to move the lever, exactly when to begin stopping. She can hit the floor level perfectly almost every time. Passengers don't realize how skilled this is. They just expect smooth rides and perfect stops. Let yourself imagine Dorothy's typical day. She arrives before the store opens, changes into her uniform in the employee's locker room, then takes her position in the elevator. She'll stand for her entire shift, 8 hours, sometimes longer. Her feet ache, her back hurts. But she stands straight, maintains a professional demeanor. The store opens, customers arrive. Dorothy's work begins. Going up, ladies' fashions 2nd floor, housewares 3rd floor, furniture 4th floor. She announces each floor, describes what departments are located there, helps customers navigate the store. Some customers are regulars. Mrs. Henderson comes every Wednesday. 3rd floor, Dorothy, she says. How's your mother? Much better. Thank you, Mrs. Henderson, Dorothy replies, moving the lever smoothly. They chat briefly as they rise. This personal connection is part of the elevator operator's job. Not just operating the mechanism, but providing customer service, creating a pleasant experience. Children are fascinated by the elevator. They press their faces against the gate, watching the shaft walls pass. Sometimes, Dorothy lets a well-behaved child help operate the lever under her guidance. The child's eyes light up with delight at controlling this magical rising room, but the job has downsides. The small elevator car becomes tedious. Dorothy sees the same walls, the same gate, the same buttons, and controls hundreds of times a day. The building's temperature varies, too hot in summer, too cold in winter. The elevator shaft amplifies sounds, grinding gears, creaking cables. Dorothy learns to identify problems by sound. A slight squeal means the cable needs lubrication. A rattle means a bolt is loosened somewhere. Some passengers are rude. Men make inappropriate comments. Women treat her as if she's invisible, discussing private matters as if Dorothy isn't there. But Dorothy remains professional, courteous, efficient. Her job depends on maintaining this demeanor. Elevator operators develop their own culture. In large buildings with multiple elevators, the operators take breaks together, share stories, complain about difficult passengers, compare their elevators. Some run smoother than others, some are faster, some have quirks that you learn to accommodate. Picture the elevator operator's break room in a busy office building in 1935. 5 operators on break, sitting in worn chairs, smoking cigarettes, drinking coffee. They compare notes. My elevator sticks between 11 and 12. Maintenance says they'll fix it, but when? I had a passenger today, must have weighed 300 pounds. Elevator moved so slow I thought we'd never reach the 15th floor. They laugh, commiserate, then return to their elevators for another shift. Breathe slowly as we enter a period of change that many elevator operators viewed with dread. Automation. As early as the 1900s, inventors had been working on automatic elevators, elevators that could be controlled by passengers themselves without an operator. The basic concept was simple. Inside the elevator car, install buttons for each floor. A passenger presses the button for their desired floor, and the elevator automatically travels there and stops. Simple in concept, but complex in execution. How does the elevator know when to stop? How does it stop smoothly? How does it handle multiple passengers wanting different floors. In 1900, a fully automatic elevator was installed in a building in New York. It used electromechanical controls to automatically travel to the selected floor and stop. But it was jerky, imprecise, and passengers didn't trust it. Most people preferred human operators who could talk to them, answer questions, provide that human touch. By the 1920s and 30s, automatic elevator technology improved significantly. Signal control systems allowed elevators to queue multiple requests. If passengers on several floors pressed call buttons, the elevator could serve them in sequence. Automatic leveling systems ensured the elevator stopped precisely at each floor. But building owners faced resistance when trying to install automatic elevators. Passengers preferred operators. Unions fought automation. Thousands of elevator operators would lose their jobs. The transition happened slowly, building by building, over several decades. Let yourself imagine an automatic elevator in 1935, early in the transition. You enter the car nervously. There's no operator, just a panel of buttons. You're not sure what to do. A sign instructs, press the button for your desired floor. You press 8 hesitantly. Nothing happens. Then suddenly the doors close by themselves. You jump, startled. The elevator begins rising. You're alone in this rising room with no human in control. What if it doesn't stop? What if something goes wrong? The elevator rises smoothly, but you feel anxious the entire ride. At the 8th floor, it slows and stops perfectly level, actually more perfectly than most human operators achieve. The doors open. You step out, relieved. This automatic elevator works, but it feels strange, impersonal, slightly frightening. By the 1950s, automatic elevators are becoming standard in new buildings. Elevator operators begin disappearing. Some transition to other jobs, others simply lose employment. The personal touch, the human element, is being eliminated in favor of efficiency and cost savings. Picture Dorothy from our earlier story, now, in 1958. She's 55 years old and has operated elevators for 33 years. The department store where she works is renovating. They're converting all elevators to automatic operation. Dorothy and her fellow operators are told they'll be let go. Some are offered positions as sales associates or stock clerks, jobs that pay less and that they're not trained for. Dorothy's last day as an elevator operator is bittersweet. Regular customers say goodbye, thank her for years of service. She operates her lever one final time, bringing the elevator to a smooth stop at the first floor, perfectly level as always. Then she removes her uniform, turns in her gloves, and walks out of the store. An era is ending. By the 1970s, elevator operators are rare. By the 1990s, they're nearly extinct in most of the world. Some remain in historic buildings, operating old manual elevators that haven't been modernized. Some remain in luxury buildings where the human touch is considered a premium service. But for most people, elevator operators become a memory, a relic of an earlier time. Relax now as we explore something fascinating, how elevators affect human behavior and psychology. Elevators create a unique social situation. Strangers trapped together in a small space for a brief time. This creates specific behaviors and anxieties. Researchers have studied elevator behavior extensively. The findings are fascinating and sometimes amusing. Picture yourself in an elevator with strangers. What do? Most people face forward toward the door, even before the door closes. Almost everyone does this automatically. Why? Partly to watch for their floor, but also because facing strangers feels confrontational. Avoid eye contact. People study the floor numbers, the ceiling, their phones, anything but other passengers' faces. Maintain maximum distance. If there are 3 people in an elevator, they instinctively space themselves out, 1 in each corner perhaps. This maximizes personal space. Remain quiet. Conversations stop or become whispered when others enter. The elevator creates enforced intimacy that feels uncomfortable. Don't face the back wall. This is so ingrained that if someone enters an elevator and faces the back wall, other passengers become very uncomfortable. Try it sometime. Face the back wall in an elevator and watch people's reactions. Let yourself imagine a strange elevator. Ride. You enter and there's already one person inside, but they're facing the back wall. Your immediate reaction is confusion, possibly concern. Are they okay? Is something wrong with them? This person is violating unwritten elevator rules, and it's deeply unsettling. Psychologists explain that elevators create forced proximity. We're physically close to strangers but have no social relationship with them. This is uncomfortable for most people. We create behavioral rules to manage this discomfort. Face forward, don't talk, don't stare, minimize contact. In crowded elevators, people often apologize excessively. Someone gets pushed slightly. Oh, sorry. No, I'm sorry. The elevator moves and people sway. Excuse me. These apologies serve to acknowledge the discomfort, to signal, I know this is awkward, I'm not a threat. Elevator anxiety is real and surprisingly common. Many people feel at least mild anxiety in elevators. For some, it's severe, a real phobia, called claustrophobia, or specifically elevator phobia. Picture someone with severe elevator anxiety entering an elevator. Their heart rate increases, they start sweating, they feel trapped, panicked. They grip the handrail tightly, they count the floors, willing the elevator to arrive at their destination. Some people with elevator phobia avoid elevators entirely, taking stairs even in 50-story buildings. What causes elevator anxiety? Several factors. The small enclosed space, lack of control. You can't stop an elevator between floors, usually. Awareness of the height. You're suspended in a box hundreds of feet above the ground. Fear of mechanical failure. What if the cable breaks? Fear of getting stuck. Elevators do sometimes malfunction. Social anxiety from being close to strangers. Some elevators try to reduce anxiety through design. Mirrors are common in elevators, and while they serve practical purposes, allowing people to check their appearance, they also serve psychological purposes. They make the space feel larger and give people something to look at other than other passengers. Music in elevators serves a similar purpose, filling the uncomfortable silence, providing auditory distraction, creating a specific mood. Elevator music became its own genre. Soft, unobtrusive instrumental music designed to be pleasant but forgettable. Interestingly, the term elevator music became somewhat derogatory, used to describe bland, boring music. But in its intended context, providing ambient sound in a potentially anxious situation, it serves a real purpose. Let yourself imagine an elevator designer in 1960 thinking about passenger comfort. We need to make people feel safe, calm. Let's add a mirror. That opens up the space visually. Let's add soft lighting. Harsh fluorescent lighting increases anxiety. Let's add handrails. Giving people something to hold on to makes them feel more secure. Let's add music. It fills the silence, provides comfort. Modern elevators often have screens showing news, weather, or advertisements. These serve multiple purposes, generating advertising revenue, yes, but also distracting passengers, giving them something to look at, reducing the awkward sense of forced proximity. Now breathe deeply, because we need to address something that causes anxiety, but is important to understand: elevator safety and emergencies. First, let's establish something crucial. Elevators are safe, extraordinarily safe. Safer than cars, safer than stairs, safer than almost any form of transportation. In the United States, about 27 people die in elevator-related accidents each year. In contrast, about 40,000 die in car accidents. You're far more likely to be killed driving to a building than riding its elevator. Most elevator deaths aren't from the cable breaking. That's the fear most people have, but it almost never happens. Modern elevators have multiple cables, each strong enough to support the elevator on its own. They have redundant braking systems. They have safety governors that detect overspeed and automatically engage brakes. The Otis safety mechanism, invented in 1852, remains part of every modern elevator in some form. So what causes elevator deaths? Most are workers killed during maintenance, about half of all elevator deaths. People crushed between the car and shaft doors. People falling down the shaft when doors opened, but the car wasn't there. Freak accidents involving moving escalators, which are technically not elevators, but are often grouped together in statistics. The most common elevator emergency isn't death or injury, it's getting stuck. Elevators stop between floors due to mechanical problems, power outages, or safety systems engaging. Picture yourself stuck in an elevator. The car stops. The lights might stay on or might flicker to emergency lighting. You press buttons. Nothing happens. The doors won't open. You're stuck. This is frightening for many people, but it's not dangerous. Elevators are designed with this in mind. The car has ventilation. You won't run out of air. There's an emergency button that connects to building security or an elevator company monitoring center. Help will come. Let yourself imagine being stuck in an elevator. It's 2 p.m. on a Tuesday. You're in an office building heading to a meeting. On the 24th floor. Around the 15th floor, the elevator stops abruptly. The lights stay on. Everything is quiet. You wait a moment. Maybe it's just stopping at a floor. But the doors don't open. You press your destination button again. Nothing. You press the door open button. Nothing. You feel a flutter of panic. You're stuck. You take a breath, look at the control panel, find the emergency button. You press. A moment later, a voice comes through a speaker. This is building security. We're aware your elevator has stopped. Are you injured? No, I'm fine, just stuck, you reply. Help is on the way. Please remain calm. The elevator is secure. Do you need anything? No, I'm okay. We'll keep this line open. Talk to me if you need anything. You wait 5 minutes, 10 minutes, it feels much longer. You sit down on the floor, might as well be comfortable. You call your boss on your cell phone, explain you'll be late to the meeting. 15 minutes. Finally, you feel a slight movement. The elevator descends slowly, then stops precisely at the next floor down. The doors open. A maintenance worker is there with security. Sorry about that, the worker says. Minor electrical problem. You okay? You step out, relieved. Legs slightly shaky from adrenaline. The whole ordeal lasted 20 minutes. Uncomfortable, yes, but not dangerous. Modern elevators have even more safety features. Many have battery backup so they'll automatically descend to the nearest floor and open their doors during power outages. They have sensors that detect obstructions in the doorway and won't close on people. They have load sensors that prevent overloading. They have temperature sensors that detect fire and automatically recall the elevator to the ground floor. Speaking of fire, elevators and fire have a specific relationship. In a fire, you should never use an elevator. Why? Several reasons. Fire can damage elevator controls, causing malfunction. Elevators might open onto the fire floor. The shaft can fill with smoke, power might fail, trapping you. During a fire, elevators are supposed to automatically return to the ground floor or a designated safe floor with doors open and then become non-operational. This is called firefighter service or Phase 1 recall. Firefighters can then take control of the elevators using special keys and use them for evacuation or firefighting if deemed safe. Picture a high-rise building where a fire breaks out on the 30th floor. The building's fire alarm system activates. Phase 1 recall. All elevators throughout the building immediately begin returning to the ground floor, regardless of where passengers wanted to go. Passengers are confused, possibly alarmed, but it's a safety measure. Once at the ground floor, the elevators open their doors and stop responding to calls. Signs light up. In case of fire, use stairs. Firefighters arrive, use their keys to take control of specific elevators, use them to transport equipment and personnel. Despite all these safety features, elevator phobia remains common. Knowledge helps some people, understanding how safe elevators truly are, understanding the redundant safety systems. But for others, the fear is deeper, not entirely rational. Picture someone with severe elevator phobia forced to visit an office on the 40th floor. They take the stairs, 40 flights of stairs, arriving sweaty, exhausted, 20 minutes late. But for them, the physical exhaustion is preferable to the psychological terror of being in an elevator. Let your mind relax now as we tour some of the world's most remarkable elevators. Not just functional machines, but engineering marvels, tourist attractions, and architectural icons. Let's start with the Beilong elevator in China, also known as the 100 Dragons Sky Lift. Picture this. You're in Zhangjiajie National Forest Park, surrounded by towering sandstone pillars that inspired the floating mountains in the movie Avatar. These pillars rise over 1,000 feet into the air. How do you get to the top? You take the Beilong elevator, one of the highest and heaviest outdoor elevators in the world. The elevator is built onto the side of a cliff, a massive glass-enclosed shaft rising 1,070 feet. You enter at the base. The glass elevator car begins ascending. Through the glass, you see the forest below shrinking, the stone pillars rising around you. In less than 2 minutes, you've ascended nearly a quarter mile vertically. At the top, you step out onto a viewing platform with panoramic views of this otherworldly landscape. The Beilong elevator opened in 2002 and was controversial. Some argued it marred the natural beauty of the landscape. But it allows thousands of tourists daily to experience views that would otherwise require hours of difficult hiking. It's also an engineering feat. Building an elevator up the side of a sandstone cliff in a remote location presented enormous challenges. Now let yourself drift to Brazil, to the city of Salvador. In the historic Cidade Alta, upper city, and Cidade Baixa, lower city, a 236-foot cliff separates the two areas. Since 1873, the Elevador Lacerda has connected them, a public elevator that's become an icon of the city. Picture taking this elevator. You're in the lower city, need to reach the upper city. You enter one of the 4 elevator cars, each capable of carrying about 30 people. The ride takes only 30 seconds, but transports you 236 feet vertically. Step out, and you've traveled from the bustling port area to the historic colonial center. This elevator isn't a tourist attraction, it's public transportation, carrying millions of passengers annually. It costs pennies to ride. Local workers take it daily. It's as normal to them as a bus or subway. Travel now to Germany, specifically to the town of Dillenburg. Here you'll find the world's first multi-directional elevator in a test tower built by ThyssenKrupp. This elevator is revolutionary because it doesn't just go up and down. It can move horizontally, diagonally, even loop around. How? Instead of cables, it uses linear motor technology, like a magnetic levitation train. Multiple elevator cars can operate in the same shaft, moving independently. Picture the possibilities. An elevator could go up 10 floors, then horizontally across a building, then up again. In buildings with multiple towers, elevators could move between towers without passengers needing to transfer. This technology is still experimental, but it represents a possible future of elevator design. Elevators freed from the constraint of only moving vertically along a single shaft. Let's visit London and ride the elevators at the Canary Wharf Underground Station. These aren't remarkable for their technology, but for their length. Picture descending an escalator that seems to go on forever. These are some of the longest escalators in Europe, descending about 100 feet into the earth. The ride takes nearly 2 minutes. Standing at the bottom, looking up, you can barely see the top. The walls of the shaft seem to converge toward a distant point. It's simultaneously impressive and slightly unsettling. You're descending deep into the earth, trusting this moving stairway to carry you safely down and eventually back up. Now, picture the Aquadome in Berlin, a hotel with a massive cylindrical aquarium in its center lobby. Inside this aquarium, containing 1 million liters of water and 1,500 tropical fish, is an elevator. You enter at the lobby level, and the glass elevator car rises through the center of the aquarium. As you ascend, you're surrounded by water and swimming fish. Rays glide past. A sea turtle swims alongside. It's magical, like traveling through an underwater world while staying dry. Tragically, the Aquadome catastrophically burst in December 2022, destroying the aquarium and elevator. But for the nearly 20 years it operated, it offered a unique elevator experience. Travel to the Gateway Arch in St. Louis, Missouri. This iconic 630-foot-tall arch has an elevator system unlike any other. The elevator cars are actually chains of small pods, 8 connected modules that rotate as they follow the curved interior. of the arch to the observation room at the top. Picture riding this elevator. You and 4 others squeeze into a small pod about the size of an airline bathroom. It's cramped and slightly claustrophobic. The door closes, you begin moving, but not straight up. You're following the curve of the arch, so the pod rotates continuously, always keeping you oriented upright, even as the angle of the arch changes. The ride takes 4 minutes. Through a small window, you can see the track you're following, curving through the arch's interior. It's strange, fascinating, slightly disorienting. Finally, you arrive at the top, 630 feet above the ground. Step out into the observation room and view the Mississippi River and St. Louis spread below. Let's visit the Eiffel Tower in Paris. The elevators here are marvels of 19th century engineering. The tower has 2 types of elevators: hydraulic elevators from ground to the 2nd level, following the curved legs of the tower, and an electric elevator from the 2nd level to the top. The hydraulic elevators are original, installed when the tower was built in 1889. Picture the engineering challenge. How do you build elevators that follow a curve? The Eiffel Tower's legs aren't vertical. They angle inward, meeting at the center. The elevator must ascend at an angle, gradually becoming more vertical. The solution involved complex lever systems and counterweights, all driven by hydraulic pressure. These elevators have been operating for over 130 years, carrying millions of tourists, a testament to their engineering quality. Finally, let's visit the tallest building in the world, as of 2026, the Burj Khalifa in Dubai. This building is 2,617 feet tall, over half a mile. It has 163 floors above ground. Ascending from bottom to top in an ordinary elevator would take many minutes and create severe ear-popping from pressure changes. The solution: double-decker elevators and express elevators. Picture taking an express elevator in the Burj Khalifa. You enter at the ground floor. The elevator accelerates rapidly, reaching speeds of 1,200 feet per minute. That's over 40 floors per minute. You feel your ears pop. Your stomach feels light. In less than 2 minutes, you've ascended over 100 floors. The elevator slows smoothly, stops at the 124th floor observation deck. You step out, slightly dazed from the speed of ascent. You're now higher than most airplanes fly at cruising altitude in urban areas. These famous elevators remind us that elevators are more than just practical machines. They're also experiences, memories, adventures. They enable us to access views and places that would otherwise be impossible for most people to reach. Relax deeply now as we explore the hidden machinery that makes elevators work. The motors, cables, counterweights, and control systems that most people never see or think about, but that represent sophisticated engineering. Picture an elevator machine room, typically located at the top of the elevator shaft or in a nearby mechanical space. This is where the magic happens. In the center of the room sits the traction machine, a large motor connected to a grooved wheel called a sheave. The elevator, cables run over this sheave. On one side of the sheave hangs the elevator car, on the other side hang counterweights. Let yourself imagine these counterweights. They're large blocks of cast iron or concrete, weighing roughly the same as the elevator car when it's carrying about 40% of its capacity. Why counterweights? Because of physics. If the elevator car going up is balanced by counterweights going down, the motor only has to overcome the difference in weight, not lift the entire elevator car. This saves enormous amounts of energy and allows for smoother operation. Picture the ballet of elevator operation. The elevator is at the ground floor, empty, called to the top floor. The motor engages, turning the sheave. The empty elevator car begins rising, pulling its cables up. On the other side of the sheave, the counterweights descend, their weight helping to pull the car up. At the top floor, the car stops. Passengers enter, making it now heavier than the counterweights. The elevator is called back to the ground floor. Now the motor works to lower the heavier car while raising the counterweights. The counterweights resist the car's descent, preventing it from falling too fast. The system is elegant, efficient, constantly balancing forces. Modern traction elevators use different types of cable systems. Traditional elevators use wire rope, steel cables made of multiple strands of wire twisted together, extremely strong. and flexible. Picture these cables. They're typically about half an inch thick, and each elevator has multiple cables, usually 4 to 8. Each cable alone could support the entire weight of the elevator. Multiple cables provide redundancy. If one somehow breaks, which almost never happens, the others easily hold. Some modern elevators use flat steel belts instead of round cables. These belts are made of layers of steel cords coated in polyurethane. They're lighter, more flexible, and last longer than traditional cables. They also allow for smaller sheaves, which means smaller machine rooms, or even machine room-less elevators, where the machinery fits in the shaft itself. Let's talk about brakes. Every elevator has multiple braking systems. The primary brake is usually a spring-applied, electrically released brake on the motor. Picture how this works. Heavy springs constantly press brake shoes against the motor's brake drum. When the elevator runs, electromagnets pull the brake shoes away, releasing the brake. If power fails, the magnets deactivate, the springs engage. The brake and the elevator stops immediately. It's a fail-safe design. Loss of power equals automatic braking. Elevators also have a governor, a mechanical overspeed sensor. If the elevator descends too fast, indicating a possible cable failure or runaway condition, the governor activates emergency brakes called safeties. These are metal wedges that deploy into the guide rails, clamping the elevator car to the rails and bringing it to an abrupt but safe stop. This is essentially Elisha Otis's original safety mechanism, refined and modernized. Picture an old elevator from the 1940s with a relay-based control system. The control panel is massive, a wall of electromechanical relays, each one a mechanical switch operated by an electromagnet. When a passenger presses a floor button, it energizes a relay. The relay closes contacts, which energize other relays in a complex sequence, ultimately controlling the motor. The system works, but is complicated, needs constant maintenance, and can't handle complex logic. Modern elevators use microprocessor-based controls, essentially computers. Picture a control cabinet with several circuit boards, LED displays, and a compact programmable logic controller. This computer manages everything: floor requests, motor speed, door operation, load sensing, emergency procedures. It can handle complex dispatch algorithms, optimize for energy efficiency, diagnose problems, record data for maintenance. The most advanced systems use machine learning. The elevator learns patterns in a building. When do most people arrive? In the morning. When do they leave in the evening? Which floors are busiest at what times? The system predicts demand and positions elevators accordingly. During morning rush hour, it might keep more elevators at the lobby. During lunch, it might position them mid-building. It continuously learns and optimizes. Let's not forget elevator doors, seemingly simple, but actually quite complex. Most elevator doors are automatic sliding doors, but they need to be precise. They must close firmly enough to seal properly, but not so firmly that they'll hurt someone caught in them. They need sensors to detect obstructions. Modern elevators use multiple sensor types, infrared light beams, ultrasonic sensors, even 3D camera systems that can distinguish between a person and an object. Picture the sequence when elevator doors close. First, the doors begin closing at moderate speed. Sensors continuously monitor for obstructions. The doors are about to close completely. They slow down, approaching the final seal position gently. They meet, lock, and only then does the elevator receive permission to move. If at any point a sensor detects an obstruction, the doors instantly reverse and fully reopen. The system prioritizes safety over efficiency. Let your breathing slow as we follow the birth of an elevator, from design through installation to ongoing maintenance. Picture a new skyscraper under construction. The steel frame is up, the floors are in place, but there are no walls yet, no windows, just the skeleton of a building. In the center, empty shafts wait for elevators. An elevator installation team arrives. Installing an elevator takes weeks or months, depending on complexity. First, workers install guide rails inside the shaft, precisely aligned vertical tracks that will guide the elevator car and counterweights. Picture workers suspended in the shaft on scaffolding, using laser alignment tools to position rails, perfectly vertical. A deviation of even a few millimeters over hundreds of feet would cause the elevator to run roughly or jam. Once rails are installed, workers lift the counterweight assembly into the shaft, a massive operation requiring a crane and careful coordination. Then comes the elevator car itself, also lifted by crane through the top of the shaft. Picture this delicate operation. A large, heavy car swinging slightly as it's lowered into position, workers guiding it, aligning it with the rails, finally securing it. In the machine room above, workers install the traction machine, the motor and sheave assembly. They run the cables from the machine room over the sheave, down to the elevator car, under the car to pulleys, back up to the counterweights. Threading these cables through the system requires precision and patience. The control system is installed. Miles of wiring connecting buttons, sensors, motors, brakes, communication systems. Modern installation includes networking cables, allowing the elevator to communicate with building management systems, send diagnostic data to maintenance companies, even call for help automatically if problems develop. Testing begins. Workers run the elevator up and down repeatedly, checking alignment at each floor, adjusting sensors, fine-tuning motor controls, ensuring smooth acceleration and deceleration. They test safety systems, deliberately triggering emergency brakes, testing backup power systems, verifying fire service recall functions. Only after extensive testing and inspection does the elevator receive certification for passenger use. Now, picture the ongoing maintenance. Most commercial elevators receive maintenance monthly. Picture a maintenance technician. Let's call him James. He's worked on elevators for 15 years, knows the machinery intimately. James arrives at an office building early morning, before peak traffic. He goes to the machine room, begins his inspection checklist. He examines the cables, running his hands along them, feeling for broken wires, a signal the cable is wearing out. He checks cable tension, ensuring all cables are equally tight. He examines the sheave, looking for wear in the grooves. He checks the motor, listening to its sound, feeling for excessive vibration, checking temperature. He inspects the brake assembly, measuring brake pad thickness. He examines the governor, ensuring its mechanism moves freely. James descends into the shaft itself, a potentially dangerous environment. He takes safety precautions. Safety harness, hard hat, lockout-tagout procedures ensuring the elevator can't run while he's in the shaft. Picture him standing on top of the elevator car, riding it slowly up and down while inspecting the shaft walls, guide rails, cables. He checks roller guides, looks for signs of water intrusion, examines door mechanisms at each floor. In the car, James tests buttons, verifies floor indicators work properly, checks emergency communications, tests door sensors by placing obstacles in the doorway. He lubricates moving parts, tightens bolts that have loosened from vibration, replaces burned-out lights. James reviews diagnostic data from the elevator's computer, looking for error codes, unusual patterns, signs of developing problems. Modern. Elevators are remarkably self-diagnostic, reporting issues before they become serious. James makes notes, schedules repairs if needed, updates maintenance records. This monthly ritual keeps elevators running safely and reliably. But between maintenance visits, problems can develop. Picture an elevator that stops working in the middle of a Tuesday afternoon. Passengers are stranded. Building management calls for emergency service. A technician must respond quickly, diagnose the problem, repair it if possible, or secure the elevator and arrange for more extensive repairs. Let yourself imagine being an elevator technician called for emergency service. You arrive at a building where an elevator is stuck between floors with 3 passengers inside. Your first priority, ensure the passengers are safe and calm. You communicate through the emergency intercom, explain that you're working on the OIKI problem, estimate how long it will take. You go to the machine room, assess the situation. Error codes on the controller indicate a problem with the door sensor on the 14th floor. You go to that floor, examine the sensor, find that it's been damaged, possibly by a cleaning cart hitting it. The sensor thinks the door is obstructed, when it isn't. You temporarily bypass the sensor, go back to the machine room, manually run the elevator to the nearest floor. The doors open. Passengers exit, relieved and grateful. You replace the damaged sensor, test the system thoroughly, restore normal operation. Total time, 45 minutes. Just another day in the life of an elevator technician. Now breathe slowly, and let's discuss something sobering but important: elevator accidents and disasters. Understanding what went wrong in the past helps us appreciate the safety of modern elevators. One of the worst elevator disasters occurred in 1945 at the Empire State Building in New York. On July 28th, a B-25 bomber crashed into the 79th floor of the building in heavy fog. The plane's impact severed elevator cables. Elevator operator Betty Lou Oliver was injured in the crash and was being transported down in a different elevator when those cables also failed. She fell 75 floors, over 1,000 feet, in an elevator car. Miraculously, Betty Lou survived. How? Several factors. The elevator's safety brakes engaged but couldn't stop the rapid descent completely. Severed cables piled up at the bottom of the shaft, cushioning the impact. Air pressure built up beneath the falling car, providing some cushioning effect. Betty Lou suffered serious injuries but lived, holding the Guinness World Record for longest. Survived elevator fall. This disaster led to improvements in emergency braking systems and in the design of elevator shafts to better contain and cushion falling cars. It also reinforced the importance of multiple independent safety systems. Let yourself imagine being Betty Lou in those terrifying seconds. The elevator suddenly dropping, your stomach lurching, knowing you're falling, unable to stop it. The sound of rushing air, of metal scraping against metal, the terror. And then miraculously waking up afterward, alive. She later said she didn't remember the fall itself. Perhaps the mind mercifully blocks out such trauma. Another significant accident occurred in 2003 in Beijing, China. A man named Li Guan was servicing an elevator when it suddenly started moving, crushing him between the elevator car and the shaft wall. Investigations revealed that proper lockout, tag-out procedures hadn't been followed. The elevator could still be called while a technician was working on it. This type of accident, sadly, remains one of the most common causes of elevator-related deaths. The lesson: rigorous safety procedures during maintenance are critical. Modern regulations require lockout, tag-out, physically preventing elevators from operating while technicians work on them. Technicians must place physical locks on control systems and carry the only keys. No one else can start the elevator until the technician removes their lock. In 2013, a horrific accident in Chile killed a young man when an elevator door opened, but the car wasn't there. He stepped into an empty shaft and fell to his death. This type of accident, though rare, reveals the importance of interlocks. Mechanisms that prevent doors from opening unless the car is actually present at that floor. Modern elevators have multiple interlocks. The shaft doors in the building can only be opened by the elevator car itself. The car doors can only open when the car is at a floor and properly aligned. These systems have redundancy, mechanical interlocks plus electronic sensors. Both must agree the car is properly positioned before doors can open. Picture these safety systems as layers of protection. Imagine each safety feature as a layer in a stack. For a catastrophic accident to occur, multiple layers must fail simultaneously. This is called defense in depth in safety engineering. One safety system fails, the backup catches it. Two systems fail, a third backup engages. The probability of all systems failing simultaneously is extraordinarily low. In 1996, an escalator accident at the Hong Kong airport killed one person and injured several others. An escalator, technically not an elevator but related, suddenly reversed direction at high speed. Passengers tumbled down. Investigation revealed a brake failure combined with a design flaw. This led to worldwide review of escalator safety systems and improvements in emergency braking. These disasters, tragic as they are, have led to progressively safer elevator and escalator design. Modern codes and regulations are written in response to accidents. Each disaster teaches lessons that prevent future disasters. Picture the safety engineers analyzing each accident, asking, what failed, why, How can we prevent this? Their work, invisible to most people, makes elevators remarkably safe. Let your mind drift now through movies, books, and stories featuring elevators. Elevators have captured imaginations for over a century, appearing in countless works of fiction. Charlie and the Chocolate Factory by Roald Dahl features the Great Glass Elevator, an elevator that can go not just up and down, but sideways, slantways, and any way you please. It can even blast through the roof and fly into space. Dahl understood that elevators represent possibility, freedom from normal constraints. If you can move vertically effortlessly, why not move in any direction? Picture young Charlie Bucket stepping into Willy Wonka's glass elevator for the first time. It's transparent, you can see in every direction. Wonka presses a button, not labeled with a floor number, but with destinations like television room and inventing room. The elevator doesn't just rise, it shoots forward, turns corners, climbs at angles. It's thrilling, impossible, magical. Dahl's elevator is limited only by imagination. The movie Speed features a dramatic scene where Keanu Reeves's character must rescue people from an elevator that's been rigged with a bomb. He rappels down the outside of the building, cuts through the elevator roof, saves the passengers just before the cables explode. It's pure Hollywood fiction. Real elevator rescues are far less dramatic, but it taps into elevator anxiety, the fear of being trapped or falling. In the horror genre, elevators feature prominently because they create perfect conditions for scares, confined space, vulnerability, no escape. The unknown when doors open. The movie Devil takes place primarily in an elevator where passengers are trapped with a demonic entity. The Lift, Dutch film, features a killer elevator with a mind of its own. Picture the classic horror movie setup. Someone enters an elevator, alone late at night. The doors close, the lights flicker, the elevator doesn't go to the selected floor. Instead, it descends, and descends, and descends, far below any legitimate floor. Where is it going? What's down there? The doors finally open to reveal something terrifying. This scenario plays on primal fears. Darkness, being trapped, descending into the unknown. In romantic comedies, elevators often serve as meet-cute locations or intimate conversation spaces. Two people stuck in an elevator together must talk, must connect. The forced proximity that makes elevators awkward in real life becomes romantic in fiction. Picture. She's a stressed businesswoman, he's a laid-back artist. They enter an elevator in an office building, don't know each other. The elevator stops between floors. They're trapped together for hours. At first they're annoyed, then they start talking, connect, fall in love. By the time they're rescued, they've found something special in that small space. The TV show Mad Men opens each episode with an animated sequence of a man falling through space, past elevator shafts, advertising billboards, office windows, a metaphor for the main character's psychological state. The elevator shaft as a symbol of falling, of being out of control. In The Shining, the flood of blood pouring from an elevator represents the hotel's violent history bursting through. Kubrick chose an elevator to deliver this horror because elevators are transition spaces, between floors, between realities, between the normal and the supernatural. Picture elevators in spy movies. They're places for secret conversations, assumed to be private. Locations for fights in confined quarters or tools in the plot. James Bond escaping enemies via an elevator shaft. Ethan Hunt rappelling through elevator cables. The elevator as an action sequence opportunity. In video games, elevators serve as loading screens disguised as gameplay. Picture playing a game where your character enters an elevator. During the ride, the game loads the next level. Maybe there's dialogue during the ride, or atmospheric music, or the character checks their equipment. The elevator serves a practical technical purpose while maintaining immersion. Elevator pitches, the concept that you should be able to explain your business idea in the time it takes to ride an elevator, have become fundamental to startup culture. Picture an entrepreneur stepping into an elevator with a potential investor. 30 seconds to make an impression, explain an idea, generate interest. The elevator's time constraint forces clarity, conciseness, impact. Relax now as we explore something often mocked but psychologically important. Elevator music and the atmospheric design of elevator experiences. Elevator music, Muzak, became the generic term, emerged in the 1920s when a company called Muzak Corporation began providing background music for elevators and other public spaces. The concept was simple. Gentle, unobtrusive music would calm nervous passengers and fill awkward silence. Picture an elevator in 1935. You step in with several strangers. Without music, the space is silent except for the mechanical sounds of the elevator. You can hear other passengers breathing. Someone coughs, it seems very loud. The silence is uncomfortable. Everyone stares at the floor numbers, desperate for distraction. Now picture the same elevator with music. Soft, instrumental music, perhaps a string arrangement of a popular song, fills the space. The silence is broken. The music provides something to focus on besides the awkwardness. Psychologically, it helps. Studies showed that elevator music reduced anxiety, made rides seem shorter, improved passenger satisfaction. But what makes good elevator music? The Muzak Corporation developed sophisticated theories about this. The music should be instrumental, not vocal. Lyrics compete for attention. Mid-tempo, not too fast or slow moderate volume. Never intrusive familiar, but not too familiar positive. In mood, never melancholic or aggressive, consistent in intensity. No dramatic crescendos or drops. The goal was music that you barely notice consciously, but that creates a pleasant atmosphere. Picture a sound designer in 1950, carefully selecting and arranging music for elevators. He's not just picking random songs, he's crafting an experience, using music as a psychological tool. Muzak even developed stimulus progression, the idea that music should become slightly more energetic throughout the workday to counteract the natural energy drops people experience. Morning music would be more subdued, afternoon music slightly more upbeat. This wasn't just elevator music, but a whole theory of how background music affects productivity and mood. Over time, elevator music became a pejorative term associated with bland, boring, unchallenging music. Musicians would complain if their work was called elevator music. But this missed the point. Elevator music was designed for a specific purpose and largely succeeded at that purpose. Modern elevators often have video screens instead of or in addition to music. Picture a modern elevator. You enter, and there's a small screen showing news headlines, weather, stock prices, advertisements. This serves similar purposes to music, reducing awkwardness, providing distraction, making time seem to pass faster. But it also generates revenue through advertising. The sounds elevators make also matter psychologically. The ding announcing arrivals, the voice announcing floors in some elevators, the particular sound of doors opening and closing. These are all designed. Engineers test different sounds, different tones, different volumes, selecting what's clear without being annoying. Picture an elevator without any sound indicators. Doors just open silently. You wouldn't know the elevator had arrived until you happen to look up and notice. The ding serves a practical purpose. It gets your attention, lets you know your ride has arrived. But the specific tone matters. Too loud and it's startling. Too soft and it gets missed. The pitch matters too. Certain frequencies are more noticeable, more pleasant, less likely to annoy after hearing them dozens of times daily. Some luxury elevators feature custom soundscapes. Picture a high-end hotel elevator, soft jazz playing, voice announcements in soothing tones, even subtle scent diffusion creating an olfactory atmosphere. Every sensory element is designed to create a specific feeling, in this case, luxury, relaxation, sophistication. Other elevators feature interactive elements. Some elevators in children's hospitals feature buttons that play different animal sounds or music when pressed. Picture a scared child going to a medical appointment. In the elevator, she can press buttons that make elephant sounds, bird chirps, silly songs. The playfulness distracts from anxiety, makes the elevator ride something fun rather than frightening. Breathe deeply now as we explore some of the fascinating physics and engineering challenges that elevators present and solve. Let's start with a simple question. How much does an elevator cable weigh? Picture a very tall building, say 100 stories, about 200 feet tall. The steel cables must span this entire height. Steel is heavy, about 490 pounds per cubic foot. A typical elevator cable about half an inch thick weighs roughly 1 pound per foot of length. In a 200-foot building, each cable weighs about 200 pounds. And remember, elevators typically have 6 to 8 cables. That's a lot of weight, 7,000 to 10,000 pounds of cable alone. This creates a problem. The cables themselves add significantly to the weight the motor must lift. When the elevator is at the bottom floor, all that cable weight is above the car, adding to what must be lifted. When the elevator is at the top, the cable weight is below the car. This varying load affects motor requirements. Engineers solve this with compensating cables. Picture this system. In addition to the main lifting cables, there are compensating cables that run from the bottom of the elevator car down to the bottom of the shaft, then back up to the counterweights. These compensating cables ensure that the total cable weight remains constant regardless of where the elevator is in the shaft. As the car rises, it has less main cable above it, but more compensating cable below it. The total cable weight stays the same, making motor load consistent. Now consider the challenge of very tall buildings. As buildings get taller than about 100 stories, traditional elevator systems face problems. Cable weight becomes enormous. Cable stretch becomes significant. Steel cables stretch under load. Rope sway from building movement becomes problematic. Elevator ride time becomes excessive. Picture riding an elevator from the ground floor to the 150th floor in a traditional elevator. Even moving at 200 feet per minute, the ride would take several minutes. For practical purposes, buildings above certain heights need multiple elevator zones. Let yourself imagine the elevator system in a 100-story building. The building is divided into zones, floors 1 to 25. Low zone elevators, floors 25 to 50. Mid-low zone elevators, floors 50, 75. Mid-high zone elevators, floors 75, 100. High zone elevators. Each zone has its own elevator banks. To reach the 90th floor, you take an express elevator to the 75th floor, exit, walk to a different elevator bank, and take a high zone elevator to your destination. This system is efficient, but requires passengers to transfer between elevators. Some buildings use sky lobbies to make this more elegant. Picture a tall building with a sky lobby on the 50th floor. Express elevators run from ground floor to the sky lobby, making no stops in between. From the sky lobby, local elevators serve specific floor ranges. The sky lobby is designed as a pleasant space. Seating, maybe a cafe, views, making the transfer between elevators less of an inconvenience. The Burj Khalifa, the world's tallest building, uses sophisticated elevator zoning. It has 57 elevators in total, organized into multiple zones with several sky lobbies. The system is complex but necessary for a building of that height. Now consider the engineering challenge of earthquake safety. Elevators in earthquake zones must handle seismic activity. Picture an earthquake striking while an elevator is in motion. The building sways. The elevator shaft deforms slightly. The elevator car could jam against the guide rails or be damaged. Modern seismic elevator systems include earthquake sensors that automatically recall elevators to designated floors and shut them down when seismic activity is detected. Flexible guide rail connections that allow the shaft to deform without damaging the elevator seismic braces and isolation. Systems special rail guides that maintain proper alignment even when the building is swaying. Picture being in an elevator during an earthquake in Tokyo. You feel the building begin to sway. Immediately, the elevator starts descending to the nearest floor. A voice announces, "Earthquake detected, elevator returning to safe floor." You feel the swaying increase, unnerving, but the elevator continues its controlled descent. It reaches the next floor, doors open, and a voice says, "Please exit the elevator and take stairs." The system has worked perfectly, prioritizing your CBO, safety. Another fascinating engineering challenge is rope resonance. Very long cables can develop wave patterns, resonance, that causes them to sway, vibrate, or even bang against the shaft walls. This is especially problematic in very tall buildings where cables are very long. Engineers use damping systems, devices attached to cables that absorb vibration and prevent resonance from building up. Wind also affects very tall buildings. The building sways slightly in high winds, and this affects elevator operation. Picture: being in an elevator in a 100-story building during high winds. The building is swaying, maybe just a few feet at the top, but it's swaying. The elevator car must accommodate this movement without jamming in the shaft or creating a rough ride. Engineers use flexible connections and sophisticated control systems that adjust for building movement. Let your breathing slow as we discuss something profoundly important: how elevators enable accessibility and independence for millions of people. Before elevators became common, people with mobility challenges faced enormous barriers. Multi-story buildings were largely inaccessible to people in wheelchairs, people with leg injuries or conditions, elderly people, pregnant women, anyone for whom climbing stairs was difficult or impossible. This meant certain jobs were impossible, certain housing was inaccessible, certain opportunities simply didn't exist. Elevators changed this. Picture a person who uses a wheelchair. Let's call him David, in 1930. An office job opens in his field on the 5th floor of a building. Without an elevator, this job is impossible for David. He cannot climb 5 flights of stairs. But the building has an elevator. David applies, gets the job, uses the elevator daily. A whole career becomes possible because of this machine. Modern accessibility codes recognize elevators as essential. The Americans with Disabilities Act, ADA, and similar laws worldwide require elevators in most multi-story public buildings. The specifications are detailed. Elevator cars must be large enough for wheelchairs, minimum dimensions specified. Controls must be mounted low enough for wheelchair users to reach. Buttons must have braille labels for blind users, visual and auditory. Announcements of floors' doors must remain open long enough for slow-moving passengers. Adequate space for guide dogs. Picture a modern ADA-compliant elevator. The button panel extends low enough that a person in a wheelchair can reach all buttons comfortably. Next to each number is braille. When you press a button, it lights up and might make a small beep for audio feedback. When the elevator reaches a floor, it announces 5th floor audibly and displays it visually. The doors stay open for several seconds before beginning to close, and they'll reopen if sensors detect someone still entering. For blind users, elevators present specific challenges and solutions. Picture someone who is blind entering a building lobby. How do they find the elevators? Many buildings have tactile guidance strips on the floor leading to elevators. How do they know which elevator has arrived? Audio announcements. Elevator on your left arriving. How do they select their floor? Braille labels on buttons, or in some modern systems, voice-activated controls. Some elevators feature raised floor markings just outside the doors, textured surfaces that blind users can detect with their canes, warning them they're near the elevator entrance. Picture a blind person walking through a lobby, their cane detecting these markings, knowing they're approaching the elevator doors. For deaf users, visual announcements are crucial. Picture someone who is deaf waiting for an elevator. Without visual indicators, they wouldn't know when the elevator arrives. They can't hear the ding. Modern elevators have illuminated arrows showing which elevator is arriving and which direction it's going. Inside the car, floor numbers are displayed prominently. Elevators also enable aging in place. Picture an elderly couple. They've lived in their apartment for 40 years. They're now in their 80s, and stairs have become difficult. If their building didn't have an elevator, they'd be forced to move. But the elevator allows them to continue living in their home, maintaining independence, staying in their community. In hospitals, elevators are literally life-saving. Picture emergency medical situations. A patient needs immediate surgery that requires moving from the emergency room on the ground floor to the surgical suite on the 4th floor. Hospital elevators are designed for this, large enough for gurneys, and medical equipment, fast, able to be summoned in emergency mode that gives them priority over regular traffic. Picture a hospital elevator in emergency mode. A code is entered or a special key is used. The elevator immediately clears any normal passengers, returns to a designated floor, and then is under control of the medical team. No stops, no delays, direct service to where needed. Minutes can mean life or death, and elevators enable rapid, vertical movement within hospitals. Modern technology continues improving elevator accessibility. Voice-activated elevators where you can say "4th floor, please," and the elevator responds. Elevators that connect to smartphone apps. A wheelchair user can call an elevator before even reaching the building, ensuring it's waiting when they arrive. Destination dispatch systems that reduce wait times and crowding, making elevator use more comfortable for people with various disabilities. Picture the future of accessible elevators. Elevators that recognize regular users through smartphone apps and automatically know their typical destinations. Elevators with sign language recognition that deaf users can control by signing. Elevators with enhanced audio environments that work better with hearing aids. The technology constantly evolves, but the fundamental truth remains. Elevators are essential infrastructure for accessibility. Relax now as we explore how elevators shape economies, property values, and urban development patterns. Here's a surprising fact. The value of property in a multi-story building typically increases with height, up to a point. Picture two identical apartments in the same building, one on the 5th floor, one on the 25th floor. The higher apartment will typically rent or sell for more money. Why? Better views, more light, less noise from street level, perceived prestige. This is only possible because of elevators. This relationship between height and value enables a crucial economic calculation. Building upward is profitable. Picture a developer deciding how tall to build. Each additional floor costs money, more materials, more construction time, more complex engineering. But each floor also generates revenue through rent or sales. The developer builds upward as long as the revenue from an additional floor exceeds its cost. Elevators change this calculation. Without elevators, the upper floors of tall buildings would be less valuable. Who wants to climb 10 flights of stairs daily? The building height would be limited to perhaps 6 or 7 floors before the upper floors become effectively worthless. But with elevators, the height limit is pushed much higher, limited now by construction costs, engineering challenges, and zoning laws rather than by access difficulty. This economic reality reshaped cities in the late 19th and 20th centuries. Picture Manhattan in 1900 versus 1930. In those 30 years, the skyline transformed from predominantly 5 to 10-story buildings to skyscrapers reaching 40, 50, even 70 stories. This was possible because elevators made it economically viable. Land in Manhattan is expensive, so building upward maximizes the revenue from each plot of land. Elevators even influence office space design within buildings. Picture an office building's rental market. Floor space near the elevator is most valuable. Less walking for people entering that office. Corner offices far from elevators are often cheaper per square foot. Smart floor plans place reception areas near elevators, maximizing the valuable near-elevator space. The elevator system itself is a significant building expense. Picture a developer planning a 30-story office building. Installing the elevator system might cost several $million, but it's necessary. Without adequate elevator service, the building won't attract tenants. The calculation becomes, how many elevators do we need? Too few, and wait times frustrate tenants, reducing building value. Too many, and you're wasting. Expensive floor space on elevator shafts that could be rented as office space. Engineers have formulas for this. Picture an elevator consultant analyzing a building plan. They calculate expected traffic patterns. How many people arrive during morning rush hour? How many leave at lunch? At end of day? They consider average trip times, door times, loading times. They run simulations. They arrive at a recommendation. This building needs 8 elevators to maintain average wait times under 30 seconds during peak traffic. Elevator wait time directly affects building value. Picture 2 identical buildings, but one has terrible elevator service, long waits, crowded cars, slow rides. That building will have lower rents, higher vacancy rates, unhappier tenants. The building with excellent elevator service commands premium rents. Elevator service quality is often mentioned specifically in office building reviews and ratings. Some premium buildings advertise their elevator systems as amenities. Express elevators to Sky Lobby, double-decker elevators, advanced destination, dispatch system reducing wait times by 40%. These aren't just technical specifications, they're selling points that justify higher rents. Let yourself imagine choosing between two office spaces. Both are nice, similar price. But one building has constant elevator problems. You often wait several minutes. The elevators are always crowded, sometimes they break down. The other building has excellent elevator service. You rarely wait more than 30 seconds. The cars are spacious and smooth riding. They're reliable. Which building do you choose? Obviously the one with better elevators. That preference translates to economic value. Residential buildings show similar patterns. Picture a luxury condo building. The developer installs beautiful, fast, quiet elevators with elegant interiors. They advertise this: custom, Italian-designed elevators with marble interiors and whisper-quiet operation. It sounds pretentious, perhaps, but to potential buyers, it signals quality throughout the building. If the developer invested in excellent elevators, they probably invested in everything. Conversely, poor elevator service in residential buildings affects quality of life significantly. Picture living on the 20th floor of an apartment building with unreliable elevators. One breaks down frequently. During peak hours, you wait 5 minutes for an elevator, then it's so crowded you can barely fit. On grocery shopping trips, you struggle with heavy bags. When you have guests, they complain about the elevator wait. This frustration affects your satisfaction with your home, might even make you want to move. Elevators also enable entirely new building types. Hotels above 20 stories are practical only because of elevators. Imagine carrying your luggage up 20 flights of stairs into your hotel room. Hospitals, airports, shopping centers, many modern building types depend on elevators. Picture the transformation of retail. In the early 1900s, department stores began installing elevators, enabling them to expand vertically. Before elevators, stores were typically 1 or 2 floors. You can't expect customers to climb many flights of stairs while shopping. Elevators enabled 5, 6, 7-story department stores with different merchandise on each floor. Third floor, ladies' fashions and accessories. This vertical organization of retail was only possible because of elevators. Let your breathing deepen as we explore modern elevator control systems that use artificial intelligence and optimization algorithms to improve efficiency. Traditional elevator systems work simply. You press up or down in the lobby, then when you enter a car, you press your floor. The system is reactive. It responds to button presses without planning ahead. Destination dispatch systems work differently. Picture approaching an elevator bank in a modern office building. Instead of up and down buttons, there's a touchscreen or keypad. You enter your destination floor, say 27. The system doesn't just call any elevator. Instead, it analyzes all elevators' positions, predicts future calls, and assigns you to a specific elevator, say car C. A display shows your assignment. You wait for car C specifically. This seems more complicated for passengers, but it's far more efficient. The system can batch passengers going to similar floors into the same car. It can balance loads across all elevators. It can predict which elevator will be free next and position it optimally. Let yourself imagine the system's logic. 10 people arrive in the lobby within a few seconds. They input destinations: 5, 8, 12, 15, 15, 22, 23, 27, 28, 31. The system thinks, car A is at floor 10, coming down with 1 passenger. Car B is at floor 3 going up, almost full. Car C is at floor 1 empty. Car D is at floor 20 going down with 3 passengers. In milliseconds, it decides, assign the people going to floors 5, 8, 12, 15, 15 to car C. They're all in the low to mid-range. Assign floors 22, 23 to car B. It's already going up. Assign 27, 28, 31 to car A once it finishes its current trip. This optimization reduces wait times, reduces travel times, reduces crowding. Studies show destination dispatch can improve elevator system efficiency by 20–30% compared to traditional systems. Picture the difference. In a traditional system, elevators often stop at almost every floor, with passengers going every direction mixed together. In a destination dispatch system, each elevator makes fewer stops, serving passengers going to similar floors. Everything moves faster. Modern destination dispatch systems use machine learning. They learn building patterns. Monday mornings see heavy traffic to floors 3–8, office spaces, lighter traffic to floors 15–20, back offices. Friday afternoons see everyone leaving roughly between 4:30 and 6 p.m. Lunchtime sees heavy traffic to floors 2, cafeteria, and 1, exit to restaurants. The system adapts, positioning elevators predictively. Picture the system on a Monday morning at 8:45 a.m. It knows from months of data that in the next 15 minutes, hundreds of people will arrive wanting to go up. So it positions most elevators at the lobby, ready to load passengers and disperse them efficiently. Compare this to a traditional system that must reactively respond to calls. The smart system is always ahead, always prepared. Some systems integrate with building security. Your access card grants you elevator access only to floors you're authorized to visit. You tap your card at the elevator panel and you're automatically assigned to a car going to your floor. You don't even need to enter your destination. Picture arriving at work, tapping your badge, a display saying Car B, and when you enter Car B, it automatically goes to your office floor. Seamless, secure, efficient. The most advanced systems integrate with smartphone apps. Picture this. You're walking toward your office building, still a block away. You tap an app on your phone, call elevator. By the time you enter the lobby, an elevator is waiting. You walk directly in, no waiting, no pressing buttons. It knows who you are. It knows your typical floor, takes you there automatically. Relax now as we explore elevators in unusual, challenging, and extreme environments, places where elevators face special difficulties. Let's start underwater. In large aquariums, elevators sometimes operate in tubes surrounded by water and marine life. We mentioned Berlin's Aquadome earlier, but the concept exists elsewhere. Picture descending through an aquarium. You're in a clear cylinder, water surrounds you, fish swimming past at eye level. The engineering challenge is significant, maintaining a watertight seal, preventing water pressure from affecting the elevator shaft, ensuring glass can withstand the water pressure. The result, though, is magical, a journey through an underwater world. In mines, elevators face opposite challenges, operating in harsh underground environments. Picture a gold mine in South Africa, one of the world's deepest mines. The mine extends over 2 miles underground. Miners must travel this distance twice daily, down at the start of their shift, up at the end. Mining elevators, called cages or skips, operate under extreme conditions. The shafts are often hot, deep underground, temperature increases. The atmosphere may be humid, dusty, or contain harmful gases. The elevators must be robust, reliable, and able to evacuate miners quickly in emergencies. Picture a mining elevator descending. You're a miner, you and 30 co-workers crowded into a metal cage. The cage begins descending, faster than any building elevator, sometimes exceeding 3,000 feet per minute. You descend and descend, knowing you're going over 2 miles underground. The shaft walls rush past. Your ears pop from pressure changes. It takes several minutes of dark, rapid descent into the earth. Finally, the cage slows, stops at your work level. You exit into the dim, hot tunnels of the mine. In extremely cold environments, elevators face different challenges. Picture an elevator in an Antarctic research station. The elevator shaft is exposed to temperatures that reach -80 degrees Fahrenheit. Regular elevator oil would freeze solid. The metals contract in the cold, affecting tolerances and alignments. Engineers use special cold-resistant lubricants, heating elements to prevent ice formation, and materials selected for extreme cold performance. In space, elevators as we know them don't work. There's no gravity to pull things down, so traditional elevator concepts don't apply. But humans have long dreamed of space elevators, tethers extending from Earth's surface to space, with cars climbing the tether, carrying cargo and eventually people to orbit without rockets. Picture the space elevator concept, a cable made of incredibly strong material, carbon nanotubes perhaps, anchored to Earth at the equator and extending 22,000 miles into space to a counterweight. Electric cars climb the cable, carrying payloads. The cars use rollers or magnetic systems to grip and climb the cable. The journey to space takes days, not minutes, but uses far less energy than rockets. It's theoretically possible, but remains far beyond current engineering capabilities. No material strong enough yet exists, and the engineering challenges are immense. In tsunami-prone coastal areas, elevators must account for potential flooding. Picture an elevator system in a Japanese coastal building. Sensors detect seismic activity that might indicate a tsunami. The system automatically recalls all elevators to upper floors, above expected flood levels. The ground floor elevator. Doors lock, preventing people from trying to use elevators to reach ground level during a tsunami. The system prioritizes keeping elevators and passengers above the danger zone. In extremely tall structures like radio towers, elevators face unique challenges. Picture a service elevator in a 2,000-foot tall broadcast tower. The structure is narrow, open to wind, swaying slightly. The elevator must be lightweight. The tower can't support heavy elevator machinery. It might use a rack and pinion system. Instead of cables, a motor driving gears that engage a toothed rail. The ride is slow, takes many minutes, and is quite exposed. You can see out in all directions as you ascend this impossibly tall, narrow structure. Some elevators operate on steep mountain slopes, functioning more like funiculars than traditional elevators. Picture an elevator built into a cliff face in Norway. It's not vertical but follows the angle of the cliff, perhaps 70 degrees. You enter at the bottom station, the car ascends at this steep angle, hugging the rock face. Through windows, you see the valley dropping away below. At the top, you exit to a viewing platform with spectacular views. These systems face challenges of operating at angles, dealing with rock stability, and handling extreme weather. Portable elevators exist for construction sites and temporary uses. Picture a construction site for a 50-story building. The building's permanent elevators aren't installed yet. They can't be until the building is more complete. But workers need to reach upper floors. A temporary construction elevator is erected on the outside of the building, a tall metal framework with a car that ascends and descends. These elevators are purely functional, open cages, no interior finish, somewhat rough riding, but they do the job. As the building is completed, these temporary elevators are removed. Let your thoughts drift now to the people whose careers revolve around elevators: designers, engineers, installers, maintainers, inspectors. Picture Maria, an elevator design engineer. She has a master's degree in mechanical engineering and has spent 15 years specializing in elevator systems. Her job is to design elevator systems for new buildings. When an architect shows her building plans, Maria analyzes how many floors? What will the building be used for? Office, residential, hotel? How many people will need to move between floors daily? During what time periods will traffic be heaviest? Maria runs simulations using sophisticated software. She inputs building parameters, estimated traffic patterns, elevator specifications. The software simulates thousands of trips, calculating average wait times, car loads, service quality. Maria adjusts variables: add another elevator, use faster cars, implement destination dispatch. She finds the sweet spot: adequate service, without overbuilding expensive elevator infrastructure. Picture the satisfaction Maria feels when a building she designed opens and the elevators work beautifully. People move efficiently between floors. Wait times are short. The building owner is happy, tenants are happy. Her design, her calculations, her decisions made this work. It's not glamorous. Most people never think about who designed the elevator system, but it's important work, and Maria takes pride in. Now picture James, whom we met earlier, an elevator maintenance technician. James's father was an elevator technician, and James joined the trade after high school. He spent years as an apprentice, learning from experienced technicians, studying elevator theory, practicing repairs. Now he's a journeyman, fully qualified, and he takes service calls across a major city. James's job is varied. No 2 days are exactly alike. Monday, he's replacing worn cables in an old building. Tuesday, he's troubleshooting electronic control issues in a modern skyscraper. Wednesday, he's performing routine maintenance on 6 elevators in a hospital. Thursday, there's an emergency call. Someone's stuck in an elevator. Friday, he's installing a new elevator car in a building that's being renovated. The job has its challenges. Sometimes James works in cramped, dirty spaces. The pits beneath elevators, dusty machine rooms, narrow shafts. Sometimes he works at heights that bother people who aren't comfortable with heights. Sometimes he works odd hours. Elevators often need maintenance outside business hours to minimize disruption. Emergency calls come at any time. 3 a.m. breakdowns don't wait until morning. But James loves the problem-solving aspect. Each elevator is slightly different. Each problem requires diagnosis. What's wrong? Why? How do we fix it? James feels satisfaction when he solves a tricky problem, when he gets a broken elevator running again, when his preventive maintenance catches a problem before it causes a breakdown. Let yourself imagine following James on a call. An elevator in an apartment building is making unusual noises. Residents are nervous. James arrives, talks to the building manager, learns the symptoms. He rides the elevator several times, listening carefully. He hears it, a rhythmic scraping sound at certain points. He goes to the machine room, listens to the motor, sounds normal. He enters the shaft, rides on top of the car, examines the guide rails as the car moves. There, he spots it. A roller on the guide assembly is worn. The bearing is failing, causing it to scrape against the rail. He orders a replacement part, returns the next day, installs it in 30 minutes, tests the elevator. Smooth and quiet. Problem solved. Another satisfied customer. Picture Yuki, an elevator inspector. Her job is to ensure elevators meet safety codes and operate safely. She works for the city government, inspecting elevators in commercial buildings. Yuki has engineering training and specialized certification in elevator safety inspection. On Seisi, a typical day, Yuki might inspect 3 or 4 elevators. She carries a clipboard with a detailed checklist, dozens of items to verify. She examines cables for wear, measures brake pad thickness, tests safety systems, verifies that door sensors work properly, checks that emergency communications function, ensures signage is correct and visible, verifies that maintenance records are current. On a typical day, Yuki might inspect 3 or 4 elevators. She carries a clipboard with a detailed checklist, dozens of items to verify. She examines cables for wear, measures brake pad thickness, tests safety systems, verifies that door sensors work properly, checks that emergency communications function, ensures signage is correct and visible, verifies that maintenance records are current. If Yuki finds violations, she has authority to order corrections, even to shut down elevators that present immediate safety hazards. Building owners take her seriously. An elevator shutdown means lost service, unhappy tenants, emergency repair costs. Yuki's job isn't to be harsh, but to ensure safety. Most building owners appreciate that she's protecting their tenants and limiting their liability. Picture Amir, who designs elevator interiors for a luxury design firm. While engineers design the machinery, Amir designs what passengers see and experience. He selects materials, perhaps polished wood panels, stainless, steel trim, LED lighting. He designs the control panel layout, chooses button styles, selects floor indicator displays. He considers color psychology. What mood does the space create? He thinks about acoustics, what materials absorb sound, making the ride quieter. Amir's designs appear in luxury hotels, premium office buildings, high-end condos. His work creates the wow factor. When someone enters one of his elevators, they're impressed by the beauty, the quality, the attention to detail. It's art meeting engineering, creating spaces that are functional but also beautiful. Breathe slowly as we consider the environmental impact of elevators and efforts to make them more sustainable. Elevators consume significant energy. In a typical office building, elevators account for 2 to 10% of total energy use. Not enormous, but not negligible. Multiply this across millions of buildings worldwide, and the impact becomes substantial. Picture the global elevator fleet, roughly 18 million elevators worldwide, running billions of trips daily. The energy consumption is massive. Where does this energy go? Motor power, lifting heavy loads against gravity, lighting inside cars' ventilation control systems and displays door motors, standby power for systems waiting in ready mode. Engineers have developed numerous strategies to reduce elevator energy consumption. Let's explore them. Regenerative braking is one of the most effective technologies. Remember that elevators have counterweights roughly balancing the car's weight. Sometimes, when a heavy car descends or an empty car ascends, the imbalance means gravity is actually helping and the motor must brake to prevent overspeed. Traditional braking wastes this energy as heat. Regenerative braking captures it. The motor becomes a generator, converting the kinetic energy back into electricity that feeds into the building's electrical system. Picture this energy flowing backwards, from elevator to motor generator, into building wiring, offsetting other electrical loads in the building. In buildings with many elevators making many trips, regenerative braking can recover substantial energy, sometimes 20–40% of elevator energy consumption. Picture a busy office building with 12 elevators. On a typical day, regenerative braking from the elevators puts thousands of kilowatt-hours back into the building's system, electricity that would otherwise need to come from the grid. That's real energy savings, real carbon emission reduction, LED. Lighting in elevator cars reduces energy compared to older fluorescent or incandescent lighting. Picture replacing old lighting in an elevator. The old fluorescent fixtures drew perhaps 100 watts. The new LED system draws 20 watts, provides better light quality, lasts far longer. Never needs bulb replacement during the elevator's remaining service life. Multiply by thousands of elevators in a city, and it's significant. Smart sleep modes. Put elevators into low-power state during inactive periods. Picture an office building at 2 a.m. A traditional elevator system keeps all systems fully powered, lights on, ventilation running, controls active. A smart system detects low traffic, puts elevators into sleep mode, minimal lighting, ventilation reduced, systems in low-power standby. A call wakes the elevator in seconds, but during sleep, energy consumption drops by 70–80%. Over a year, this saves substantial energy. Destination dispatch systems, beyond improving service, also save energy. By batching trips efficiently, the same number of passengers reach their destinations with fewer total trips, less distance traveled, less energy consumed. Picture the math. Traditional system makes 1,000 trips in a day to move everyone. Destination dispatch system accomplishes the same movement with 800 trips. 20% fewer trips means roughly 20% less energy. Some modern elevators use gearless permanent magnet motors, more efficient than traditional motors, wasting less energy as heat. The improvement might be 30–40% better efficiency. Picture replacing an old elevator's motor with this new technology. The old motor drew 20 kilojoules to move the elevator. The new motor draws 12 kilojoules for the same movement. Over the elevator's 20-year remaining life, that's enormous energy savings. Material. Choices in elevator construction also affect environmental impact. Picture choosing between steel cables and synthetic fiber belts for an elevator. The synthetic belts last longer. Less frequent replacement means less material consumption over the building's life. Weigh less, reducing the energy needed to lift the cables themselves, and are recyclable at end of life. Small choices like this, multiplied across millions of elevators, create meaningful environmental impact. Some elevators now use carbon fiber components instead of steel where possible. Lighter. Weight means less mass to accelerate and decelerate, meaning less energy consumption. The carbon fiber costs more initially, but pays back over the elevator's life through energy savings. Solar-powered elevators exist, though they're rare. Picture a remote location, perhaps a scenic overlook in a national park. An elevator transports visitors from a parking area to a viewpoint. Solar panels on the nearby visitor center generate electricity stored in batteries, powering the elevator. The system is off-grid, sustainable, leaving no environmental footprint beyond the structure itself. Environmental considerations also include the energy and carbon footprint of manufacturing and installing elevators. Picture the full life cycle: mining iron ore, smelting steel, manufacturing components, shipping them to construction sites, installation, decades of operation, finally decommissioning and recycling. Forward-thinking manufacturers analyze this full life cycle, working to reduce impact at every stage. Some companies now offer elevator modernization specifically focused on energy efficiency. Picture an old building with 1980s-era elevators. They work, but are energy hogs. A modernization project replaces motors, installs regenerative braking, upgrades controls, adds smart features. The elevators work better than before and use half the energy. For building owners, the energy savings pay back the modernization cost over several years, then continue saving money and carbon for decades. Green building certification systems like LEED include elevator efficiency as a factor. Picture a building pursuing LEED certification. The design team specifies high-efficiency elevators because this contributes points towards certification. This creates market incentive for efficient elevator technology. Building owners want certification, so they demand efficient elevators. So manufacturers develop better technology. The system works. Let your mind drift now into possible futures, where elevator technology might go in coming decades. We've mentioned multi-elevators briefly, the ThyssenKrupp system that uses linear motors instead of cables, allowing horizontal and diagonal movement. Picture buildings designed specifically for this technology. Instead of elevator shafts being separate service cores, they're integrated throughout the building. Elevators move up, across, down, diagonally, following complex three-dimensional paths. You enter an elevator on floor 1 of Tower A. It rises to floor 10, moves horizontally across a sky bridge to Tower B, rises to floor 30, moves horizontally again to Tower C, rises to floor 50. One ride, no transfers, taking you on a three-dimensional journey through a complex of buildings. This technology could enable entirely new architectural forms. Buildings that branch, merge, cantilever, spiral. Forms that would be impractical with traditional vertical elevator shafts. Picture cities of tomorrow with interconnected high-rises, elevators moving between them, creating three-dimensional transportation networks in the sky. Autonomous elevators that adapt to individual users. Imagine elevators that recognize you, through facial recognition or your smartphone. They know your patterns, your preferences. You typically go to floor 23 for work, but on Wednesdays you go to floor 8 for a weekly meeting. The system learns this. On Wednesday mornings, when you approach the elevator, it already knows to take you to floor 8. It plays your preferred music, adjusts lighting to your preference, bright and energizing in morning, softer in evening. It's your personal elevator experience, customized specifically for you. Voice-controlled elevators will become more sophisticated. Picture simply saying, "Take me to the executive conference room," and the elevator knows where that is, takes you there. No button pressing required. Or, "I need to meet with Sarah Chen," and the system determines Sarah's current floor, from building security data, routes you there. Natural language understanding makes elevators intuitive, even for visitors unfamiliar with the building. Predictive maintenance will advance. Modern elevators already report diagnostic data to manufacturers. Future systems will use AI to predict failures before they happen with high accuracy. Picture an elevator that notices a bearing's vibration. Signature has shifted slightly, too subtle for human inspection to detect. AI analyzes the pattern, predicts, this bearing will fail in approximately 73 days. Maintenance is scheduled. The bearing is replaced during planned downtime, preventing an unexpected breakdown. The result? More reliable elevators, less downtime, lower maintenance costs. Transparent elevator shafts might become common in buildings designed for impressive views. Picture an elevator car that's mostly glass, traveling through a shaft that's also glass. On the outside of a building, you're essentially riding on the building's exterior, with panoramic views in all directions. Some luxury buildings already have this, but cost and safety concerns limit adoption. As materials improve and costs decrease, more buildings might feature this dramatic approach. Maglev elevators using magnetic levitation instead of cables are being researched. Picture an elevator car with no cables. It's held and propelled by powerful electromagnets. The advantages: no ropes to wear out or replace, potentially faster speeds, ability to have multiple cars in one shaft moving independently, no height limit imposed by cable weight. This technology exists in prototype, but isn't yet practical for commercial buildings. But perhaps in 20 or 30 years, cable-free maglev elevators will become standard. Personal rapid transit systems that are essentially horizontal elevators might become common. Picture a large campus, university, corporate headquarters, airport, hospital complex. Small automated pods on tracks move people between buildings. It's like an elevator, but horizontal. You tell it your destination, it routes you there directly, no stops, unless other passengers in your pod have nearby destinations. This exists in limited forms, airport people movers, but could expand dramatically. Elevator-based emergency evacuation systems might be developed for very tall buildings. Currently, elevators aren't used for evacuation during fires. You take stairs. But in a 150-story building, descending 150 flights of stairs is exhausting, impossible for many people, and time-consuming. Future buildings might have specially designed evacuation elevators, pressurized shafts that resist smoke, backup power systems, fireproof construction, priority override in emergencies. Picture a fire on the 100th floor of a super-tall building. Designated evacuation elevators automatically go into emergency mode. Provide protected, rapid descent for occupants from floors above the fire. This technology is being developed and might become required in the tallest buildings. Space tethers, the space elevator concept, remain a distant dream but are actively researched. Picture Earth decades from now. A tether extends from an equatorial platform up through the atmosphere, through low Earth orbit, all the way to geosynchronous orbit, 22,236 miles up. Climber cars attached to the tether, using solar power or beamed power to ascend over several days, carrying payloads to space far more cheaply than rockets. It sounds like science fiction, but physicists believe it's theoretically possible. The challenges are immense. Material strength requirements beyond anything currently manufacturable, risk of catastrophic failure, cost, time to build. But if achieved, it would revolutionize space access. Everything we've discussed about elevators, safety, efficiency, control systems, passenger experience, would apply to these space elevators at a scale that's hard to imagine. Let your breathing become very slow and peaceful now as we return from the future to the present and reflect on what elevators mean. We've traveled through time in this story, from ancient Egyptian hoists to possible space elevators. We've explored technical details, human stories, cultural impacts, future possibilities. But let's return to something simple: the everyday experience of riding an elevator. Picture yourself tomorrow, entering an elevator. Maybe you're going to work, or visiting someone, or shopping. You press a button, the doors close, the elevator moves up or down. 30 seconds later, the doors open, and you step out at your destination. It's so mundane, so ordinary, that you probably won't even remember the ride by evening. But take a moment to appreciate what just happened. You traveled vertically, something that would have been impossible for most of human history. You covered perhaps 100, 200, 300 feet in half a minute with zero physical effort. You didn't climb stairs, didn't get tired, barely noticed the journey. You were in a sophisticated machine, tons of steel and electronics and controls, all working precisely to carry you safely. Sensors monitored your safety. Control systems ensured smooth motion. Brakes stood ready to engage if needed. Maintenance, performed weeks ago, ensured reliability. Picture the chain of human effort that made your elevator ride possible. Engineers who designed the system, workers who manufactured components, installers who assembled everything precisely, inspectors who verified safety, maintenance technicians who keep it running. All these people, most of whom you'll never meet, contributed to your 30-second journey. Consider what elevators enable in your life. Maybe you live or work on an upper floor that would be impractical without elevators. Maybe you have mobility, challenges that make stairs difficult. Maybe you're carrying heavy items. Maybe you just appreciate not having to climb stairs multiple times daily. Elevators, invisible infrastructure that we rarely think about, shape our daily lives in fundamental ways. To picture cities without elevators, they'd look completely different. Low-rise cities, spreading horizontally instead of reaching vertically. Many jobs wouldn't exist. Many opportunities wouldn't be accessible. The modern urban environment we know, dense, vertical, efficient, exists because of elevators. Think about the moments elevators have been part of your life. Moving into a new apartment, riding the elevator with your possessions, going to job interviews, nervous elevator rides to unknown offices, visiting friends in high-rises, taking children to see city views from observation decks, quiet conversations in elevators with colleagues, awkward silent rides with strangers, celebrations after weddings or events, crowded into elevators in formal clothes, laughing and talking, hospitals, elevators to visit new babies or say goodbye to dying relatives. Every significant building in your life probably had an elevator, and that elevator was part of your experience, even if you didn't notice it. Picture future generations. They'll have elevators we can barely imagine. Faster, smarter, more efficient, perhaps going directions we can't conceive. But the fundamental purpose will remain the same: moving people vertically, overcoming gravity, enabling access, connecting spaces. Elevators are more than just machines. They're enablers of possibilities. They're infrastructure that supports modern life. They're the reason buildings can rise into the sky. They're how cities can be dense and vertical rather than endless sprawl. They're access for everyone regardless of physical capability. They're thousands of small journeys every day that collectively enable our lives to function. So next time you ride an elevator, perhaps take a moment to appreciate it. Notice the smooth acceleration, the precise stop, the sensors that make sure the doors don't close on you. Think about the engineering, the maintenance, the design that makes it work. Appreciate that you live in a time when vertical travel is effortless, when buildings can touch the clouds, when accessibility is enabled by machines that work reliably billions of times every day. From ancient Roman platforms lifted by slaves to modern computer-controlled systems, from Elisha Otis cutting his own safety cable to prove a point to sophisticated AI systems that predict where passengers want to go before they ask. It's been an incredible journey. A journey upward, always upward, lifting humanity higher. And now let yourself drift peacefully, like an elevator, ascending slowly through a quiet building at night, rising gently, smoothly, effortlessly. No destination in particular, just the peaceful sensation of rising, of floating upward, carried safely by invisible forces. Sleep well, knowing that somewhere in the world, at every moment, millions of elevators are carrying people safely upward and downward, enabling lives, connecting spaces, defeating gravity one ride at a time. The story of elevators is the story of human ingenuity, of our refusal to accept limitations, of our determination to reach higher. It's a story that continues, rising ever upward, like the elevators themselves. Rest now. Float peacefully. Rise gently into dreams. Sweet dreams. Picture one final elevator ride. It's late evening. A building somewhere. It could be anywhere. The lobby is quiet, dimly lit. You're alone as you approach the elevators. You press the button, the familiar ding. Doors slide open with their gentle whisper. The car is empty, inviting. You step inside. The doors close with a soft thump, that sound of sealing, of separation from the world outside. For a moment, you're in this small room, this transitional space. Not where you were, not yet where you're going. Just here. Present. The subtle hum of the motor. The soft vibration through the floor as the elevator begins to move. You feel it. That slight pressure change, your weight shifting almost imperceptibly as acceleration begins. Your stomach registers it, that curious sensation. We've all felt so many times but rarely stop to notice, rising, moving through space, defying gravity. The floor numbers change, 3, 4, 5. Each one a story of the building passing, another layer, another level, another set of lives and rooms and purposes. The elevator knows where it's going, knows how to get there, knows when to slow, when to stop. All you do is ride, trust, let it carry you. 7, 8. The air is cool, the lighting soft. Maybe there's quiet music playing so subtle you barely hear it. Or maybe there's just silence, peaceful silence. The sound of the machinery so familiar, it becomes part of the silence rather than breaking it. 10. You notice your reflection in the polished metal door. You notice the texture of the handrail. You notice the certificate on the wall. Inspection. Passed, next inspection due in some future month. Evidence of care, of maintenance, of systems working as designed. 12. Higher, always higher. Above the trees now if there are trees, above the streetlights. Into the realm where night is darker, where city lights spread out like stars fallen to earth. 14. 15. The elevator slows. That gentle deceleration, your weight shifting forward, almost imperceptibly. The precision of it, stopping exactly level with the floor within millimeters. The work of sensors and motors and control systems and careful engineering. Perfect alignment. Every time, the doors open, you step out into a quiet hallway. Behind you, the elevator doors close. The car waits, ready. Ready for the next passenger, the next journey, the next rise. Somewhere in the building, the elevator begins another trip. Somewhere in the city, hundreds of elevators are rising and falling like breath, in and out, up and down, endlessly cycling. Somewhere in the world, millions of elevators are carrying people through their days and nights, and you're exactly where you needed to be. The elevator brought you here, safely, reliably, unremarkably. As it always does, as it always will. Rest, now in the knowledge that these machines, these remarkable machines, will be there tomorrow. Ready to carry you upward once again, ready to help you rise. Float gently now into sleep, like riding an elevator into dreams. Smooth, safe, peaceful. The doors close softly, the world fades, you rise into rest. The end.